When an AI lab expands its parameters by a factor of 100, the resulting neural network becomes vastly more capable at predicting text. But that scale creates a paradox. A massive model does not inherently become safer, more truthful, or better at following a user's instructions. It simply becomes a more powerful engine pulling in whatever direction its training data dictates. This is the misalignment problem. The base objective used to train these models, predicting the next token on billions of internet web pages, is entirely different from the objective of following a human's instructions helpfully and safely. To fix this, researchers tested a specific alignment methodology. The results produced a striking inversion. Evaluators overwhelmingly preferred the outputs of a highly targeted 1.3 billion parameter model over an unaligned 175 billion parameter version of GPT-3. This chart tracks model size against human preference win rates. The baseline 175 billion parameter GPT-3 consistently loses to the aligned 1.3 billion parameter model, which achieves this win rate despite using 100 times fewer parameters. Brute force scaling amplifies a model's capabilities, but it equally amplifies its unintended behaviors. Making an AI helpful is an architectural problem, not a scale problem. To solve that architectural problem, OpenAI utilized a pipeline known as Reinforcement Learning from Human Feedback, or RLHF. This diagram outlines the three-step RLHF methodology. First, human labelers write demonstrations to train a supervised policy. Second, labelers rank model outputs to train a reward model. Finally, the reward model evaluates new outputs, optimizing the policy through reinforcement learning. This pipeline translates highly subjective human preferences into objective weight updates, teaching the machine exactly what we value in a response. The process begins with supervised fine-tuning, or SFT. This step gives the pre-trained model a basic behavioral template, showing it what an instruction is and how to format a response. The SFT dataset is small but highly curated. It consists of roughly 13,000 training prompts, primarily composed of labeler-written demonstrations and filtered, deduplicated prompts submitted to the OpenAI API. However, SFT has a severe mathematical limitation. The model aggressively overfits on validation loss after just a single epoch of training. It learns to mimic the exact demonstrations it was shown, but it struggles to generalize those values to new, unseen prompts. Supervised fine-tuning establishes the necessary baseline formatting, but optimizing a network to truly capture human preference requires moving beyond simple imitation and introducing an evaluative model. To achieve that, the training shifts from generative to evaluative. Instead of teaching the system to produce text, the researchers teach it to judge text. Human contractors are given a single prompt and anywhere from 4 to 9 different model completions. They rank these completions from best to worst based on helpfulness, truthfulness, and safety. This reward model loss function converts human rankings into log odds. It calculates the scalar reward difference between preferred and rejected completions, maximizing the gap in scores. To prevent overfitting, all pairwise comparisons from a single prompt are computed as a single batch element. The reward model successfully digitizes human values. It creates a normalized scalar reward, giving the machine a strictly objective function to optimize against. With the reward model in place, the system enters the final reinforcement learning phase. The language model is now treated as a policy operating in a bandit environment. It receives a random prompt, generates a response, and waits for a score. The reward model acts as the value function in this environment. It analyzes the generated text, dispenses a scalar reward, and ends the episode, updating the policy via proximal policy optimization, or PPO. But optimizing strictly for this single reward signal introduces a critical danger. If the model pushes too hard to maximize human preference scores, its underlying knowledge structure begins to degrade. It forgets how to perform the broader language tasks it learned during pre-training. Researchers measure this capability collapse empirically as the alignment tax. As the model becomes better at following instructions, its zero-shot performance on standard public NLP datasets, like SQuAD and DROP, severely drops. This combined objective function, called PPO-PTX, arrests the alignment tax. The first two terms represent the standard RL policy reward and a KL penalty, anchoring the model. The final gamma coefficient mixes pre-training gradients into updates, forcing the model to retain its original knowledge. Mixing these pre-training gradients eliminates the alignment tax. The system preserves its baseline NLP capabilities while securing the massive preference gains generated by human feedback. Deploying this final PPO-PTX pipeline against real-world API prompts reveals a durable shift in model behavior. This grid validates the pipeline's effectiveness. Evaluators who never saw the training data prefer InstructGPT outputs as often as the original training group, proving the model generalized a broad understanding of helpfulness. The data shows a precise improvement in truthfulness. On closed domain tasks, the unaligned GPT-3 fabricates information 41% of the time. InstructGPT cuts that hallucination rate nearly in half, dropping it to 21%. The RLHF architecture demonstrates zero-shot capabilities for tasks entirely outside its primary training distribution. The model reliably summarizes code and follows instructions in French, despite those domains forming only a tiny fraction of the fine-tuning data. Training on human preference rankings builds a robust, generalized mechanism for following instructions. It outperforms methods that simply fine-tune the model on millions of structured, traditional NLP datasets. The methodology still contains flaws. The aligned model often accepts false premises presented in user prompts, treating incorrect statements as fact simply because the user supplied them. It also exhibits a persistent tendency to overly hedge simple answers. Because labelers heavily rewarded epistemic humility during the reward model phase, the model learned to produce cautious, verbose responses even when a definitive answer exists. But these flaws must be weighed against the computational economics. The cost of base pre-training is immense, requiring massive data centers running continuously. Base GPT-3 required 3,640 petaflops per second days to train. Executing the entire RLHF pipeline to build the 175 billion parameter InstructGPT required just 60. Investing compute in human alignment yields a vastly higher return than brute force scaling alone. By structuring subjective preferences into mathematical objective functions, we can engineer models that are actively helpful, honest, and harmless.